All right, continuing on with our work on linear functions. In this video, we'll be looking at scatter plots and trend lines, also known as lines of best fit. This is one of my favorite pieces of linear functions because it's just so real world. And there's also always a little bit of real world error or real world scatter in our data, so nothing ever ends up perfect, which is kind of refreshing, I think. So we'll start off with an introduction, which in this case is really just a set of steps I think you should follow for finding a line of best fit by hand. And then we'll do one example and we'll check our work on Desmos. Okay, so presumably you're given a table of X and Y data that are real world data that aren't perfect data. And so your first step is just to plot the points and look at the pattern, and maybe the data aren't in a linear pattern. In the examples we'll look at today, they will be, but don't just automatically fit a line to data if they don't show a linear pattern, okay? So you need to do some thinking. Draw a line through the points. That doesn't mean you need to connect 2 points. You want to roughly have your line go through the middle of the points and follow the general trend of the data. But there are no hard and fast rules to follow. There is a formal algorithm called linear regression that will always get you the sort of the best fit of a line. But when we're fitting a line by hand, we're going to eyeball it a little bit and we'll all get slightly different answers. And then also don't let an outlier have too much influence on a line. Sometimes a point doesn't really fit the trend, and you might want to force your line to accommodate that point as well, but you need to have use a little bit of judgment and think about, should that point overly influence the line or not? Maybe it was a bad piece of data, maybe it's real valid data, and you need something that's not a line to fit to your data. We're going to figure out what the equation is by picking a couple points your line goes through, and you'll use a couple of far apart points to do so. Don't pick 2 points that are super close together. And then think about your slope and y-intercept. Do they make real world sense? All right, before we do that though, let's look at a couple examples of correlation coefficient. Correlation coefficient is a number between -1 and 1 that tells you how good of a fit your line is to your data. We will not be calculating correlation coefficient when we find these linear functions by hand, but any technology app that you use to do linear regression and to find the line of best fit will give you the correlation coefficient. A correlation of +1 and a correlation of -1 means you have a perfect match, a perfect fit between your data and your line, and that's rare in the real world. The positive just means your line has a positive slope, and the negative just means your line has a negative slope. This is a little bit misleading here, this image that I found. Here it says r is -1, but in reality, if r was -1, all the points would lie perfectly on the line. They would be exactly on the line, and here it's not. So in this case here, r is actually maybe more like, I don't know, -0.9 or something, okay? But if your R value is negative, that doesn't mean you have weak correlation. If your R value is close to 0, it means you have a weak correlation. So in this middle graph right here, there's really no pattern to the points. It's just like a shotgun blast of buckshot shot at the graph, right? There's no pattern at all. They're not in a line, and so there's very, very low correlation. Let's do one example, and this is a house painting example. I found some data on the web that take the size of a house as the input variable and help us predict what the painting price might be. So you can imagine this actually being a real world scenario. You're a painting company and you want to give quotes over the phone for how much what the cost of painting the house will be, and all you need to ask them is what's the square foot of their house, and that will give you a pretty good estimate of what the cost will be to paint the house. The challenge here is to plot the points and make a scale. Okay, so we'll go and try do that right now. Looks like we need to have a max value on the x variable. This is x, this is y. Max value of x is about 3,200. So 1, 2, 3, 4. I'm going to go up by Let's have this be 1,000. 1, 2, 3, 4, 2,000. 1, 2, 3, 4, 5, 3,000. And let's see if we can make a little space here. 1, 2, 3, 4. Yeah, so this will be 3,200 right here. Okay, so that fits. It looks like we need to go up to about 4,200 here. 1, 2, 3, 4, 5. So this is dollars. This is square footage. 1, 2, 3, 4, 5. 2,000. 5, 3,000. 5, 4,000. And 4,200. So let's plot that 4,200, 3,200 point. So that's our biggest house right there. Over 1,300 up 2,000. That's going to be right there. Again, the most time-consuming part is just plotting the points. Over 2,000 up 3,000. It looks like points are falling in a straight line, so that's kind of nice. 900, 1,400 is right there. 1,200, 1,800 right there. 1,500, 2,000 right there. 2,200, 3,100 is way up here. And 1,400, 1,700. You know, I probably could have plotted these points ahead of time and made our video a little bit shorter, but I think it's actually helpful to show you that it takes a bit of time to plot these guys, and I don't want you to rush through it. I want you to be careful with it. 1,400, 1,700 right there. All right, so looking at our data, it looks like we have a rough linear trend, and I'm going to try to draw a line. It's something like that. Seems pretty good to me. So again, there's no hard and fast rule. You want to roughly split the points on either side. You want to roughly follow the trend of the data. It looks like we did pretty okay right there. And then let's find a couple clean points that aren't necessarily actual data points your graph goes through that we could use to plot to find the equation. I'm going to pick those two just because they're nice clean points. So this is 600 and 1,000. And this guy over here looks like 2,800 and 3,800. So let's find an equation, okay? Slope is difference in the y's, and I'm going to subtract large minus small, minus 1,000, over the difference in the x's, 2,800 minus 600. And I'm going to turn that into a decimal right now. So 2,800 divided by 2,200. So I have a slope of 1.27. I want to check that. Yep, slope of 1.27. Let's think about what that means. It means every additional square foot in your house costs $1.27 to paint. Okay? So you can think of it as dollars per square foot. I'm going to call it just M. Let's pick a point and plug in and find B. So y equals mx plus b. So 1,000 equals m, 1.27 times our x value of 600 plus b. So let's go ahead and solve for b and subtract that from both sides. So once we multiply the 1.27 times 600 and then subtract it from the 1,000, we end up with a 238 equals b. Okay, and let's continue our line down here. Does that sort of make sense? Are we getting roughly 200? Yeah, that looks like it could be about 238 right there. Okay, so we have an equation, y equals 1.27x plus 238. Okay, so if you were that painting company, you would use that equation to give estimates. Let's do a quick flip to Desmos, and I've already input everything into Desmos and found the best fit equation, and let's compare. Let's see how we did. So in Desmos, we will plot our points on a table, and then use this form y1 with the tilde mx1 plus b, and it gives us some variables. Unfortunately, I can't highlight or point on the screen right now, but you can see in the upper left that m is equal to 1.27. Is that exactly what we got? That's really nice. So we got 1.27 also. That's great. Let's check the 238. It looks like Desmos gave a B, you can see in the upper left, of 228. So really pretty close. I feel like we did a pretty good job. Let's turn on that line, and you can see that it fits the data pretty well. All right, so I feel like we did okay with that, and that is just a great place to stop right there.